our topic is about passive transport and active transport. Now we know about passive transport that the ions or the solute particles, they diffuse from high concentration to low concentration. And if we take in consideration about active transport, we know that from low concentration the ions are getting transport through a protein molecule to a higher concentration with the help of energy molecules. This is the knowledge that we all know about from our previous classes, but today we will discuss about how biophysics is correlated to this. First of all, we should take a consideration of a membrane transport, naturally, which is a homogeneous membrane, and it is started with thermodynamics with a reference to molecular structure of the membrane and transport mechanism. If we The homogeneous membrane is the simplest model, which is in contact with two solution, as I shown here, solution 1 and solution 2. The dissipation function instead the element dx. Now a small dx of a membrane is taken, which is written in the form of T sigma eta of j, defined by mu I, where ji, this is the flux, ji is the flux, vector flux of ith component. Like if there is a membrane, if there is a this whole membrane which is shown to you, now the jth component or the ith component through the membrane, mu I is the chemical potential, and integration expression will be taken of this as a phi. What is phi is written as a function, dissipation function, which is to be calculated. Now if we take talk about if we talk about if we take a integrated dissipation function, and if we want to calculate how the membrane and two solvents on the two side, the one having medium mu1 and the other having the medium coefficient as mu2. So here we know that phi phi sign is equals to j, which is the flux, del p, which is the overall difference in the pressure, and jv is the diffusion flux, and jv is the total volume flow, and del pi is what? Del pi is the difference in the osmotic pressure. So if we calculate this all, so we come to know that the x which comes out, the x which comes out is the reflection coefficient, and which is same for what? If we see for rbc, the x is a constant, which is 0.62. This comes out to be 0.62, the volume of the number of erythrocyte x, reflection coefficient. Now if we go to the what we say, ionic ionic equilibrium is nothing but we have to calculate the number of moles of ions of potassium, number of calcium, and chloride and potassium, how these are related to thermodynamics. Now if we take in consideration phenomenological non-equilibrium thermodynamics as applied to passive ion transport. Passive ion transport is built up by analogy with the description of the transport of neutral molecule. The phenomenological coefficients are also expressed through the friction coefficient. Now if we take in solution of NaCl in water, the calculations are simplified if the membrane is strongly charged, and therefore the concentration of fixed counter ion in the membrane is higher the concentration of the neutral salts. Now if we take in non-thermodynamic equilibrium, we say offers a physically substantiated description of passive transport. If we take, like, if there is a sodium ions, then we know that Then we know how the concentration of sodium ions and the potassium ions move practically freely in the exoplasm like any membrane of the living matter. That is why their concentration gradient are determined by the special properties of membrane rather than by specificity of cytoplasm. The resting potential, that is the potential difference for the excited membrane, unexcited membrane, characterizes a certain non-equilibrium steady state process. We shall first consider the ionic equilibrium. Now, if we take into concentration that if the non-equilibrium, so by that with the help of Nernst equation we can say that and we derive a formula which is psi is equals to RT by F. F here is a Faraday constant, R is also a constant, and T is the temperature. Ln pk plus pna, the pk that is for potassium, pna for sodium, pcl for chloride. Now if we take, this is the ionic equilibrium, and the permeability coefficient, what is pk, is given by pk. Now these are all the pk, that is permeability coefficients for sodium, potassium and chloride. And by all of these we came to know we all can drive Hodgkin's Cad's formula from this. It agrees well with experiment at large CEK and small CIK. When CEK decreases or CIK increases, the value of the quantity, that is del phi, tends to certain the limit. The product PKCIK behaves as a constant and increase in the resting potential. Therefore, the permeability coefficient that I told you PK, theoretical models are also constructed to overcome the activation barriers of the ions that traverse the membrane. Now if we take into, now we will come to the active membrane transport, how this is transported and how all of this takes place. Now we know that ATP is required for the transport of ions through the protein molecule to the other side of the membrane. An increased concentration of potassium ions and a decreased concentration of sodium ion inside the cell are determined by active transport, membrane transport, which proceed against the electrochemical potential gradient. As you can see, I am drawing a membrane here and I will show you how basically the active transport takes place. Active transport is one of the most important features of life processes. In this, it is accomplished through the coupling of diffusion fluxes to the exergonic reaction that takes place in the bulk of the membrane. The transfer of matter occurs at the expense of the free energy liberated in the chemical reaction. Energy of the hydrolysis, energy which is obtained on the hydrolysis of ATP. The coupling indicated is not trivial. As we can see, the coupling coefficients for scalar and vector fluxes are equal to 0 in an isotropic system in accordance with Curie principle. Okay, the coupling of chemical reaction to diffuse may be indirect, arising as a result of a stationary state being maintained. On the other hand, direct coupling is also affected to the anisotropy of membrane. Now we can say that facilitated by a chemical reaction which is known as facilitated or mediated transport. In this case, the transport of accelerated due to the presence in the membrane of carrier substances. Now you can see here this yellow color, this is a carrier substance which interact with the transport ions or molecules. Ion or molecules form a complex with the carrier on the other side of the membrane. This complex is broken side on the inner side. You can see the ATP is required for the transport of sodium and potassium ions. Now here C is the carrier. As you can see, this is how potassium and sodium ions are influxed and effluxed out and inside of the cell. If we see the equation which is related to this, we will see that C is the carrier, S is the transported substance, okay, which leaves the membrane, and Cs is the complex which is formed. The following reaction takes place inside the membrane. This is the reaction which is taking inside the membrane. the flux of the S passes through the membrane from the stationary state condition, it follows that the flux of the carrier in the membrane, that is Jc. What is Jc is the flux of the carrier. It is compensated by opposing flux of complex Cs, that is circulation of C occurs. Let us consider if there is a connection, sodium pump is there, then transporting mechanism operative in the membrane, in the which makes use of free energy of ATP for the active ions. So this is how carrier transporters, they react with they require ATP and the CP, which is, what is CP is the product, what is they phosphorylated carrier or dephosphorylated carriers. Now ATP is the product which is left over. Now if we come to the ionic balance and ionic exchange, so we will know and we will come to the equation how all of this is taking. The ionic exchange coefficient, it is equal to Ki Ne upon Ke and Na. These are the concentration, of potassium and sodium ion inside and outside of the cell. The phenomenological relations, now these are the phenomenological relation which will relate through it. Okay, from this we know how ATP is used and how through ionic calculation and applying the thermodynamic processes and the laws, how the biomechanics of transportation take place. If we come to the flux, how flux is derived, we can see from here. This is the membrane which I am drawing. I is the outside of the ions and I is the inside of the ion and E is the outside of the ion. Okay, now here you can see this is the jk. This has you the first circle. This is the X and Z. X, it goes in X direction, the flux, and it comes down in Z direction. The flux from that come from in Y direction. The jk is the flux of potassium ion. JNA is the flux of sodium ion, and JNY is the flux of sodium ion in Y direction, that is phosphate. The exchange of ion, accordingly we introduce the stoichiometric coefficient P, V and X, different from unity. Here the JNA and JK, that are the passive fluxes, the coupling of fluxes is shown here, how it works, and we will from that the coupling of the fluxes, and by whole lot of equations we derive that here Ci and C, these are the dimensionless concentration of the ion inside and outside of the cell, referred to the molar concentration of water in corresponding volume. So from all of these equations we derive that JKCINA raised to the power eta and Cx raised to the power x eta Ki, these are the initial concentration of what takes place, the flux, the in a stationary state, the right state, how the right handed sides are equal to the 0. In the cell only ATP, that is X, is used up. From the first two equations that we see is follows that the active efflux of sodium from the cell is determined by the reaction velocity Cx. Cx here is the velocity and is compensated for the stationary state by the passive flux, that is of sodium ions. Now by all of these we derive the equation which is called the kinetic which is known as kinetic model, which agrees with the flux which is 0 to, that is these flux will help in how the sodium and the potassium ion are transported in active transport system.